Fair lady,
Hello, how are you?
I'm good. I'm here. How about yourself?
I'm good. I'm good.
All right, let me share my screen. Well, first I gotta get this PowerPoint opened up. All right. Let me share my screen right quick, and then well, no, we'll wait for. We'll go ahead and get cracking. All right. So we are kind of taking a step back. Um, when we talked about molecular orbital theory, we didn't talk about the Diels-Alder reaction. And I want to talk about that now because it has a lot of faces to it. There's a catalysis angle that we're going to look at. There's a asymmetric catalysis angle that we're going to look at. There is a chiral starting material angle that we're going to look at. There's a, I mean, it just has a lot of different. It's been studied from a lot of different perspectives, other than just the typical molecular orbital uh, considerations, right? So the Diels-Alder is a four plus, what we call a 4+2 cycloaddition. We've seen that before. You have a 4-pi system and a 2-pi system that react together. It's what you call pericyclic. So it's just like in the same vein as uh, in the same vein of a Koch rearrangement or a Claisen rearrangement, or one of those sigmatropic rearrangements where the electrons move over a specific set of atoms. So it's pericyclic. There is a homo-lumo interaction. The homo of the diene and the lumo of the dienophile interact. We talked about that when we dealt with MO theory, dealing with like the how to increase the rate of a reaction where molecular orbitals are involved is you perturb the homo or the lumo, right? You can add a donor to the homo, or you can add a acceptor to the lumo to lower its energy, donor to the homo to raise its energy, so that you lessen the gap between the homo and the lumo. So we already talked about that. And the reactions between the diene and the dienophile, which we're going to talk about. And the dienophile is just when you see that suffix phile from the one of the Greek words for love, philos, is a lover of dienes, right? So it's diene and dienophile interacting. And if you add, in this particular case, if you add a donor to the homo, it's going to increase the rate of the reaction. If you That should be lumo, not lump. If you add an electron withdrawing group to the lumo, that will increase the rate of reaction. So this is a basic Diels-Alder reaction between 1,3-butadiene. In order for you to do the Diels-Alder, you have to have a conjugated diene, right? That's one of your main reactants. You got a conjugated diene, and then you have some uh, dienophile. That dienophile doesn't have to be a double bond. It can also be a triple bond, or it can be a carbonyl in some cases. If you're doing a what is it, heterodyls-Alder reaction, then the diene can be um, the dienophile can be a carbonyl. All right, so you can see here, if you take the diene and react it with this dienophile right here, and we conjugated this with a carbonyl to increase the rate. The overall outcome of the reaction is a 6-member ring, a 6-member cyclohexene. So you can see where you have a 6-member core, and then you have your a new alkene here, right? So the way this works is here, the mechanism, right? You have electrons flowing between both the diene and the dienophile. So this pair of electrons is going to make a new carbon-carbon bond here, and then this pair of electrons is going to make a new carbon-carbon bond here, and then this pi bond gets shifted over. So that's where that pi bond comes from in the product. So it's pericyclic. So you got this cyclic redistribution of electrons, and then it's one step, and it goes through a cyclic transition state, which is shown here. So you can see right here, this is the HOMO of the diene. If you remember back to when we were looking at 2 pi, 4 pi, 6 pi systems, uh, this is based on standing wave theory, and is also based on this particle wave duality between of an electron. So that's how we develop the molecular orbitals for a given system. And this uh, molecular orbital here is the HOMO for a conjugated diene. All right, so you get new carbon-carbon bonds, and you also, again, in the transition state, there has to be overlap between the HOMO of the diene and the LUMO of the dienophile. So you can see right here, uh, there has to be constructive overlap as well. We talked about that before. So the signs of your lobes have to match in order for there to be constructive overlap and a sharing of electrons. All right, so for your uh, dienophile, you can, again, if you put a an acceptor, if you conjugate it with an acceptor, it's going to be more reactive because that's going to lower the energy of the LUMO. So here you can see like if it's just a plain alkene, that's the slowest out of all of these. And then if you put a chlorine on or some halogen that's acting as an acceptor or an electron withdrawing group, it's going to increase the rate, but it won't increase it as much as adding a carbonyl like an ester or amide or aldehyde, or even you can even this could even be a ketone. It doesn't matter. That carbonyl group, it has a huge dipole going towards oxygen, so it's going to activate this carbon right here, the terminal carbon in the alkene, for to accept a pair of electrons from your dienophile. I'm sorry, from your diene. And then maleic anhydride, which is here, very good, uh, highly reactive alkene, um, and it's a great dienophile for the Diels-Alder. And then you can again, I said earlier, you can also use alkynes as dienophiles, right? They work just as well. And it depends on what your desire is for your product. Alkynes give you multiple pi bonds in the product that you can also work with and functionalize. So it depends on what your product needs are. Um, so there's another aspect to this reaction, and that is stereospecific, right? It is whatever your dienophile stereochemistry is, it has to be maintained in the product. So if the dienophile is cis in the product, the substituents that are on your dienophile are also going to be cis. If it's trans, then in the product, the substituent is also going to be trans, right? That's a consequence of the transition state. We go back to here, right? So this is, sorry about that. This is going to come either from the top face, or it can also attack from the bottom face, which is where the asymmetric catalysis part comes in at. Because again, if we want asymmetry and we want to induce some type of chirality, then we have to have a bias in the transition state, right? Where there are two competing transition states. We need a bias that's going to favor one over the other. So we're going to talk about that a little bit later. But here, the diene is coming from the top face. It can also come from the bottom face. And that's where your stereospecificity comes in. This happens and it's polar, so there's no opportunity for bonds to rotate or to change their conformation or anything like that. So that's why it's stereospecific. And then you have that stereochemistry is maintained in the product. All right. So if it's cis over here, then it's gonna be cis over here. If it's trans over here, it'll be trans over here. Now, if these are if these groups are different, then the stereoisomer that you get, right, you're gonna actually get a mixture of stereoisomers if this is ends up being a racemic mixture. But because this is symmetrical, right, there's no chirality. But when when the groups are different, then you have the opportunity for chirality. But because there's no bias, you're going to get basically two stereoisomers in equal amounts, unless you introduce a bias. There's also another, it's a stereochemical, but there's also an electronic um, consideration for the Diels-Alder, and that is whether or not the product you get is endo or exo, right? And so you see this with cyclic dienes. If you have a cyclic diene, then you have this observation of the endo versus exo product. And if you look at this in 3D, right, when you react this cyclic cyclobutadiene or cyclopentadiene, sorry, with this dienophile, right, you see here you get two products. One where the carbonyl group is on a dash, meaning it's underneath the ring system, the fused ring system, because you can see here you're going to get a fused ring system, or one where it's above it or on the outside. So that's where your two products come from. You have the endo product and the exo product. And for situations like this, the endo product is usually favored, right? And the reason it's favored is because of right here, right? You can see that the pi bond, the carbonyl pi system here, is able to align itself with the pi system here. So that's what this drawing here is indicative of. So you have a pi system here, you got a pi system here. Anytime you can have that type of pi overlap, you're going to get some stabilization. All right. And so when you have that type of overlap and stabilization, that's called a secondary orbital interaction. That's going to tend to favor, in these cases where you have endo and exo, it's going to tend to favor the endo if there's a functional group on your dienophile that's amenable to these secondary orbital interactions, right? So endo is favored, exo is not necessarily disfavored, but it's not as favored as the endo because you don't get that extra stability that you get when you have these secondary orbital interactions possible here. Are any questions up to this point?
No, sir.
So you have the transition state to think about, the homolumal interactions. You have um, the ability to increase the rate by adding a donor to the dienophile or an acceptor to the, I'm sorry, a donor to the diene or an acceptor to the dienophile. You have the stereospecificity aspect to think about, and then the endo-exo aspect, right? So uh, there's also, when you think about the regiochemistry, right? Interest kind of grew in being able to control the regiochemistry, right? So if you look at your if you look at your diene, right? Again, we said if you put a donor on the diene, it's going to activate that diene. If you put an acceptor on the dienophile, it's going to activate the dienophile, right? But you can see here, regiochemically, you can have two different products, right? Two separate products. You can have product A, where it's just standard electron demand, or you can have product B, which is what we would call inverse demand, right? And that is something that's also been studied. We're going to talk about that. I don't know if we'll get to the inverse demand today, but we'll definitely have an opportunity to talk about it. Uh, but we have for the regiochemistry, you can control it by perturbing either of the substrates by changing their electronics. And again, if X is a if Y is a donor and X is an acceptor, then you're going to see product A predominate. If X is an acceptor and Y is a donor, then you're going to see product B predominate. So you can have these uh, inverse electron demand Diels-Alder where you can control or even control the regiochemistry. Uh, and here's the way to think about that inverse demand, right? If you have a acceptor on your diene and a donor on your dienophyte, which is shown over here, right? That's going to give you that's going to give you the inverse demand. If you have a donor on your diene and an acceptor on your dienophyte, that's normal demand. And if you look here, if it's just neutral, then there's no regiochemistry to consider, right? But everything is going to be dependent on the homo-lumo gap, right? Right here, you can see the gap between the homo and lumo, and if you remember, those are the orbitals that have to interact in the transition state in order for this reaction to occur. So you got your donor, acceptor, homo lumo interaction here, and then if it's inverse demand, then it's the opposite, right? It's the homo of the dienophile reacting with the lumo of the diene, right? And you can see that that's a bigger gap. So with the inverse demand, there may be more uh, of a necessity of some type of catalyst, like a Lewis acid or a Lewis base, or some type of catalyst that's going to decrease that homo lumo distance. And then you can see here under neutral conditions, there's also a significant energy gap between those. But most of the time, um, when you do Diels-Alder with the homo-lumo interaction, all these reactions are done. Majority of them are done under thermal conditions, right? So you have to add some energy to that system in order to get that reaction to happen. All right. Any questions about that? About the homo-lumo interaction, inverse demand, anything? We're going to talk more about the inverse demand, and we're going to talk more about the regiochemistry um, this week, because today we'll probably just get into the Danishefsky's dying, which was a very important discovery, and then we'll get a little bit more into the asymmetric catalysis of it, and then we're also going to talk about the hetero Diels-Alder as well as um, other types of Diels-Alder reactions. All right. So this is one example. This was published by Evans, and if you look at the date, right, they've been studying this reaction for a long time. A long time. If you look at the date from 1972, this was done by Evans. They were synthesizing morphine analogs and the morphine backbone, which you know is a tricyclic system, uh, like an alkaloid type backbone. And so what they were studying was the 4+2 cycloaddition of this diene and this dienophyte. And if you notice, it's set up for like an inverse demand Diels-Alder, right? And then they did another step where they did a sigmatropic rearrangement to convert this into the necessary backbone. Right. So so if you look here, it's really set up like an inverse demand, right? So this is an electron withdrawing group or an acceptor, and then over here you have a nitrogen that's bonded to your uh, dienophile. So that's, nitrogen is a good donor. So you expect it to be like inverse demand 4+2. So that's what's going to dictate the regiochemistry, right? So you're going to alter that regioselectivity by putting these groups on here. And so that's what they were able to do. And once they achieved the cycloaddition here, then they were able to do the rearrangement. I think that's a typo. I think this shouldn't be here in this version of it, but I'll fix it before I upload it. Uh, they're able to do a 2,3 sigmatropic rearrangement to get to this product, which was a precursor to the final morphine backbone. But the point is that they were looking at the dying and putting some type of an acceptor group on here to see if they could dictate the regiochemistry, and they actually were able to do that. And this was back in the 70s. So uh, the next logical idea, and you can see how closely together these papers are. This is by Samuel Danishefsky. This was published in 1974, right? So he developed this what's called the Danishefsky's Diene, and if you his concept was that he wanted to look at expanding the utility of your dying, right? A lot of work had gone into looking at what we can do with the dienophile to make it better, make it more reactive. But up to this point, there had not been a lot of studies done on the Diene itself. So his idea was to put a donor at either the one position right here, which would activate position 4 through either through resonance or induction, or put a donor at position 3, which would also activate position 4, right? And then study the effects of what type of donors and what type of functional groups here, uh, how they would alter the outcome of the reaction. So with his the hypothesis was that the donor should increase both reactivity and regiospecificity, right? And we already know that if you put a donor on the Diene and the Diene is reacting through the HOMO, it's going to increase the energy of the HOMO and by concomitantly close the gap between the HOMO and the LUMO, right? Uh, so the donor is going to increase reactivity and regiospecificity. That was the idea behind it. Uh, and then you have also functional groups now in your cyclic product that can act as precursors for other synthetic targets, right? And one of those targets is to be able to eliminate the Z group right here, whatever Z is, right? Eliminate it through beta elimination. So you can see here, you go from here to just adding a proton source, and then you do beta elimination by, I can I annotate that? Yes. So you'll put, if you had pair of electrons on X, you push those here, here, and like that. I'm sorry, that's kind of sloppy, right? So that's your beta elimination pathway. So they were really looking for, again, just like with the Evans chemistry, how they were looking for a way to do the 4+2 and then have some other reaction kind of cascade and follow that. In their case, it was a 2,3 sigmatropic rearrangement. In this case, they were looking for ways to further functionalize, because the idea was to have the not have the cycloaddition product be the last thing that was there, right? And you want to, again, anytime you develop a method, you want to also have an application for it. So they're looking long range, like, okay, I got this cycloaddition product, but what if I wanted to use this strategy in a total synthesis or some other type of uh, synthetic pathway? I need to make sure that I can further functionalize this or do something else with it, right? So you can do their idea was to either have it go through a beta elimination pathway or just a simple protonation, right, at the alpha site to whatever this group is. Now, normally this group is the X is the oxygen. All right. So this was in 74. And let me clear this off. Right. So the Danishefsky dying looks like this, right? So you can actually start with this compound here. It's like what they call a vanillagous ester, and it is commercially available, treated with triethylamine to enolize that alpha site. We've seen that before, right? Uh, and zinc chloride is necessary as a Lewis acid catalyst to activate the carbonyl, and then you just trap the enol with TMS chloride. Uh, at first, they tried just doing triethylamine and TMS chloride, but it was not successful. So they had added in that zinc chloride as a Lewis acid, and then they were able to get out this diene, this highly functionalized diene, in 68% yield. Right, so this is ubiquitous in organic chemistry. This Danishefsky's diene. This is has been used by a lot of different groups for a lot of different applications. Um, and then if you look here, these are all the different applications that they studied in this one particular paper in 1974. All right, so they looked at the Danishefsky diene with cyclic dienophiles like maleic anhydride, and they got uh, this bicyclic product in good yields. All I think, let's see, all of the yields in this case are somewhere between 50 and 75%, if I'm remembering correctly from that publication. So again, with the anhydride, maleic anhydride, they were able to get this cyclic product in good yield, right? And again, you can see now you can further functionalize this. If you consider deprotecting here, then you have a ketone here that's able to be functionalized, and you could also uh, act on the methoxy group that's here, right? They also studied the diene with alkynes, and in this reaction, they're able to get this uh, cyclic diene, right? It's not conjugated, obviously, but they get this cyclic diene, which undergoes aromatization when it's treated with a proton source, so acid, so weak acid, and it actually aromatizes from here to here when it's treated with a weak acid. Um, so this is a really clever way to synthesize substituted aromatic compounds. All right. Also, the diene, when treated with just methacrylene, uh, obviously you get a six-member cyclohexane that's substituted here. And you can see here the methacrylene reaction is going to give you this with the enol, the solid protected enol. Then you treat it with weak acid to deprotect that enol uh, and reveal that eventually convert that into the carbonyl, right? So that's another reaction that they looked at. This was actually again good, very good yields. All these have really good yields, right? Same thing here. If your dienophile uh, is substituted with an aldehyde with the Danishefsky's diene, that works as well, right? So you can see these are all good, very good precursors to other products, right? So you have an ester here that you can functionalize. You have an alkene here that you can functionalize, or carbonyl. Same thing here. You have an aldehyde that's functionalizable. You can use it in another reaction, and then you have another alkene here or a carbonyl here, right? And then they also tested this particular diene, the Danishefsky diene, with this quinone type species here, right? Reacted that, you get the obvious product, and then you could also consider what would happen if you reacted this with two equivalents of the Danishefsky diene, then you'll get a tricyclic system, right? But with one equivalent, you get this cyclic, bicyclic system right here. And if you treat that with acetic anhydride, then you're able to actually aromatize that and get this aromatic naphthalene derivative here, right? So this diene has a very wide reaction scope, and um, it also has high reactivity, right? So what they expected was for it to be highly reactive. They also expected it to be um, reactive with a broad range of substrates, and they actually proved that. So this was again published back in 1974. So rather than go into, well, I'll give you the introduction to the asymmetric cycloaddition, but we're gonna also talk about hetero-Diels-Alder reactions like the azo-Diels-Alder. I'm gonna include that, and also we're gonna talk about those inverse demand Diels-Alder reactions. I want to bring that up before we get into the asymmetric part, but I can introduce the asymmetric part, and then we're gonna stop, and then we'll come back to the hetero-Diels-Alder as well as the um, so hetero-Diels-Alder and the inverse demand Diels-Alder. We'll talk about both of those before we get deep in the weeds with these asymmetric versions, right? But what I do want to talk about, like how the asymmetric Diels-Alder kind of evolved from intramolecular Diels-Alder reactions with pre-existing chiral centers. We'll talk about that first, and then we're gonna talk about, like, obviously we're moving towards uh, chiral catalysts and things like that. So if you recall, right, if you want to do a reaction asymmetrically, or make it do it such that you have a chiral product and not a racemic mixture of products, right? You need to have either a chiral substrate or you need a chiral catalyst, and both of those are serve the same purpose. They introduce a bias in the transition state for that reaction. Um, and then, so if you have a chiral substrate, then it's expected to maintain the chirality, but simply because of the how specific the reaction is, and the known pathway, right? How the homo and lumo overlap and interact. You might have competing transition states, but you expect it to maintain that chirality as long as your chiral center is not on the reactive site. Um, so you can direct that using that chiral center, and then a number of catalysts that have been developed to do asymmetric 4+2 cycle additions is just it's unreal. But we're only going to touch on a few of those examples, but not today. Um, so initially, and you can see when this seminal work was done in 1982. This was done by Philip Fuchs, and his the concept was to use a Z diene, right, to limit the number of transition states. That was the first idea behind, their intramolecular 4+2, and doing it such that the products are chiral and isolated in high enantiomer selectivities. And by limiting the transition states, then you decrease the obviously the mixture and the product distribution. So what the proposal was that if they used Z dienes, then that really would only be able to go through one particular transition state, whereas the use of E dienes opened up, I think in the paper they mentioned about that there were four possible pathways with the E diene. So if you're able to do it on a diene that limits the competition, then you should expect high enantiomer selectivity and enantiomer specificity. And so what they used was this chiral amino diene. So here's your diene right here, right, and then here's your nitrogen, which is really from an amide, and I'll show you how they actually made that compound. I think it's in here. Actually, I didn't put it in here yet. All right, so I'll show you that part too, adding the transition states, but I'll have to switch to a different document. But when I upload this, it'll be in the PowerPoint. All right, so here's your chiral uh, diene. You can see the chirality here, right? And then you also have chiral centers back here on the backbone. And then here's your dienophile. And all of these were synthesized separately and then merged together. And then the cyclization happened, right? So so over here is your product, and you can see here you've set multiple chiral centers based on the chirality of this center right here, right? So you got two chiral centers here, you got two chiral centers here, and then these chiral centers were already set prior to the reaction, right? So let me switch to a different document. Oh, right there. And I just didn't get a chance to paste this uh, in, but it'll be in when I upload this PowerPoint to Blackboard. I guess on this one. Right, so this was the model system that they used right here. This is how they synthesized that amide, by the way. So they took this carboxylic acid and they basically did an amidation reaction with this diene. And you can see this is the chirality here is already set. This was the model system that they used before they looked at the main system that I showed you on the other slide. So amidation here to give you this amide. And then when they took this amide, now they talked about like multiple pathways to get to these two products, but the main pathway transition state is shown here. And I'm this all.
Russ, can you switch screen?
Oh yeah, hold on. Sorry about that. What about now?
Yes, sir. I see
All right,
it.
thank you. Thank you for letting me know. All right, um so this is the diene, it's chiral at this site right here, and then this is your acid. And so the amidation reaction took place between these two functional groups to give you this uh, diene that is amenable now to intramolecular 4+2 cycloaddition. So just the standard cycloaddition pathway is going to give you this compound right here. And usually X is an alkoxy group. So it's either like an OTMS group or a methoxy. I think they have four different substrates that they looked at. Um, so this X group is some type of alkoxy group, and this is the main product from 4+2 cyclization here. And I didn't get a chance to finish the transition state. I was working on that down here, but you can see it right here. So this is the transition state, and this is the orientation of your diene right here relative to your dienophile, right? So this is the predominant transition state where you have this cycloaddition happening here. And then what you end up with is a tricyclic system like this, right? Where the actually the amide is here in a fused ring that's fused with the six-member adduct here, and then the other six-member ring, which was already present right here, is now here, right? But this was your dienophile, and then your amide cyclizes all together. So right here, when you form the six-member ring, and let me zoom in on that. And I'm redrawing these because this is kind of hard to decipher. But it's almost like a chair-like transition state where your diene is here, your dienophile is on the backside. So the diene is actually attacking from the top face of the dienophile, and that's going to give you your main product, which is right here, right? And this is the product that was expected. What they also saw was a minor product right here, where it went through kind of a hetero Diels-Alder pathway, where instead of the alkene being your dienophile, it actually ended up being the carbonyl. So that's why this transition state is for the CO, that's the carbon oxygen fuse ring or carbon oxygen fusion. So right here, this is where your Diels-Alder took place. So between these 2 atoms here, and then these 4 atoms here. So that's where you get this other minor product from right here, right? And that's only seen when the X group is an alkoxy group right here, right? So this is kind of, and out again, this is kind of a redrawn transition state of this, but you can see right here, it's the carbonyl, and then that, and the alkene now, I'm sorry, the diene now is coming from the back phase and overlapping with the carbonyl. And all of these transition states come as a consequence of being able to rotate around this carbon nitrogen bond right here, this carbon carbon bond right here, and then the carbon carbon bond here. So you can rotate around those bonds to access all these different conformations. So in the paper, and I'll post the paper as well. I'll post all the references that are in this presentation. But in that paper, they talked about how there was access to multiple transition states, and they're all kind of equilibrating with each other. But the main transition state that gave you the main product was this one, and then the other transition state that gave you the side product, and it was only formed in a small amount, but it was still showing up. It would be this one, whether carbonyl is your dienophile. So I'll have all this uploaded and uploaded to Blackboard, and I'll upload the video to um, YouTube. But for now, we'll stop. We're going to come back, talk about the hetero Diels-Alder, the azo Diels-Alder, and then we're going to talk about some inverse demand Diels-Alder reactions on Wednesday. Then we're going to come back to the asymmetry part.